Okay, so the next section is section 7.4, lengths of curves. The homework I will give you at the end of the section, probably not tonight. Alright, so think about it like this. Lengths of curves is also called the arc length because you are basically measuring the length of an arc. If you remember, you've done this before, but without calculus. If you remember pre-calculus, you had to find the arc length given the theta and a radius, and then the arc length was called S. Okay, but here nothing was changing. It was a set area on a circle, and it was a small measurement, and we knew the degree. Now, of course, if I wanted to figure out right here the length of this arc or this curve, what do you notice is that it's changing over time. And remember that calculus is the study of change. So anytime we want to find something that is changing over time, you better believe it that you're going to be using calculus to do this. So if we walk along a curve with a GPS device, we have a pretty good idea of how far we've gone. If we will walk along a curved path and have only the equation of the function along whose path we travel, a much more likely scenario, then we use a calculus to find how far we've gone. Okay, so of course this will never happen, but you're in calc class, right? So we can approximate our distance by dividing our paths into several equal partitions and sum the distance. Okay, so we're approximating the distance that we have traveled by breaking up that path into equal partitions, and then we can add all of these distances between the points, and we'd get our distance, our total distance. But of course it's an approximation, which is usually what calculus is. You already know where this is going, so to achieve a better and better approximation, what can we do? We can take smaller distances, but of course now we're going to have distance plus distance plus distance plus distance, so it's going to be a lot of different equations. So here the limit process will emerge again. Now, this finite process with the limit attached becomes a very simple integral. Because remember, when you're finding the limit, you're actually finding the derivative, and then, when you're finding the limit as things get smaller and smaller, you are basically setting up the derivative when you're adding up sums. The integral. So here's how it's derived. So let's remember, if we wanted to find the distance between 2 points, so we want to find this distance right here, what formula do we use? Think back to Algebra 2. If you recall, it was the distance formula. And if you remember that the distance formula is when you do x2, right? So let's call this guy x2 and y2, and then this guy is x1, y1. So what you do is you take x2, subtract it from x1, and then you add that to the difference of y2 minus y1. Essentially, the distance formula is basically finding the hypotenuse of the Pythagorean theorem. So let's remember, how do we do that? How do we find c? If this is change of x and this is change of y, it's the same thing as basically saying that the distance is equal to change in x squared plus change in y squared. I just rewrote the problem. Now, this is not the only distance that we need to find. So if this is one distance, we're going to separate all of them in equal partitions, and we're going to add them all up. So that's like taking the sum of all of these equally partitioned distances, we can say from A to B, right? So our function is from A to B. So this next part where it says to achieve a better and better approximation, we take smaller and smaller line segments. So think about it like this. You take a line segment from here and here, and of course they have to be equal, so I'm dividing this bigger line segment into smaller pieces. And then you would add them all up, but of course that's tedious. So we have an equation to figure out the length, the approximate length of the arc that starts off with this idea, and then eventually we're going to use the definition of limits. So basically what this is saying is that the length of the arc, we're going to use this curly QL, the length of the arc is equal to the limit as n approaches infinity. So these distances are going to become shorter and shorter from a equals 1 to n, however many partitions we use, of the distance formula, which is change of x squared plus change of y squared. Now, in order to use calculus for this, we remember, do you guys remember how limits and integrals are related? So, just a little side, when you have the limit as n approaches infinity of a function, which is, this is our function, times the change in x, okay, however you're dividing it. This can be rewritten, the sum of the functions times the change in x from a to b. Then this can be rewritten as the integral from a to b of f of x. And what is change in x? Change in x is just the same thing as saying dx. So this is where we want to get to. We want to take this sloppy looking equation that does use the definition of limits and change it to an integral. Okay, so the first thing that we spot is that we somehow need to get this change in x in our problem, but I don't want to just place it here. So what I'm going to do is I'm going to use some algebra, some tricky algebra, to kind of place it without really changing the problem. So what we can do is multiply by change in x times change in x. And what is that? That's just, so I placed it. But by placing this 1 divided by change in x, I basically just multiplied this whole thing by 1. So I'm not really changing anything, right? But this way I have placed this guy right here. Now I need to move this part right here. So all of this is the proof, okay? This is the proof of how they got the arc length. So I need to move this into the radical, okay? So if I wanted to move it into the radical, that means place it in the radical. I can't just take the square root, right? Algebraically, I don't want to change this problem. So if I square the top, which 1 squared is just 1, and square the bottom, did I change anything? What's the square root of anything squared? It's just itself. But by doing this, what I just did is I'm able to rewrite this problem. And then I'm not going to keep rewriting this, just know that this is kind of following all the way down. So now what I have is the square root of the change in x squared plus the change in y squared. Now inside the radical, because it's multiplied, I can bring it in, times 1 over the change in x squared. So this whole thing got multiplied by that, and then this guy is on the outside. So let's clean this up a little bit. Change in x squared times 1 over change in x squared is what? 1 plus change in y squared over change in x squared is just change in y squared over change in x squared, and then the change in x. Now, the closer we're getting to this integral, because we have all of these changes in x's and y's, let's rewrite them using the dx dy format. Because remember that change in x, and dx mean the same exact thing. So if I rewrite this guy as dx, because that's what change in x is, and then in here I have 1 plus change in y, which is what? dy over change in x, and of course this whole thing is squared. What does that look like? What is dy dx when they ask you to do that? It's the derivative. So let's continue our path right here. I'm going to rewrite that L. So L equals the limit as the partitions get smaller and smaller from a equals 1 to n, or to b, okay, however, from a to b, sorry. And then this is going to be 1 plus, instead of writing dy dx, I'm just going to write f prime of x, because that's the derivative. And of course that derivative is squared, times dx. So now do I have the format? I have the limit with the sum, I have the function, and I have my dx. So now I can change this and rewrite it as the integral so that the length of the arc is equal to the integral from a to b of the square root of 1 plus the derivative of f of x squared dx. So there's our proof of how they started off with saying, okay, let's divide this into equal line segments, add them all up, take the sum of them. But if we do that, then we can basically take a better approximation using calculus. There's our proof. So, arc length, L, sometimes it's called S, or aka the length of the arc of a function from x equals a to x equals b is given by this formula. And yes, you do have to memorize this formula. Okay? Sorry for the sniffles, but it is sick season. Okay. Example 1. I'm walking along a path defined by y equals ln secant of x from x equals 0 to x equals pi over 4. So here's my path. Here's my path from the calculator screen. And you're walking along from x equals 0. And let's call this guy right here pi over 4. I want to find out the length. So now we are no longer talking about the area under the curve. We want to figure out how far am I walking from here to here. So now we want to give an exact and approximate answer, and we're going to use our formula. So our length is going to be from where to where, 0 to pi over 4, of the square root of 1 plus the derivative of the function. Okay? So we need to find the derivative of this function. So actually before, well, let's just do it right now. So it's the derivative of ln of secant of x squared dx. So side work, of course, what do you got to do? I'm going to find the derivative of this function. What's the derivative of ln of anything? It's 1 over that something. So ln of something is 1 over that something times the derivative of that something. And what is the derivative of secant of x? Secant x tan x. So what happens here to secant x and secant x? They're gone, so our derivative that we're left with is just tan x. So now I can actually continue on solving this. So it's from 0 to pi over 4 of the square root of 1 plus tan x squared, right? dx. Now right now looking at this, there's nothing that we know that we've learned that can help us figure out how to integrate that. We don't know the integral of tan x squared. We don't know, so if you try to break it up, you can't. In the calculator, of course, you'd be done. Just plug it in and get your answer. But if it wasn't on a calculator part, then this is where it gets a little tricky because there's two things that you have to recall for this example. So first off, what does this look like? If I wanted to simplify this problem, what does it look like? The Pythagorean identity. 1 plus tan squared x equals secant squared x. So I can simplify it by saying from 0 to pi over 4 of the square root of secant squared of x. And then of course, when you take the square root of anything squared, then it's just 0 to pi over 4 of secant of x. Now if you remember, this was actually one of those harder problems that we did a while ago. I'm not gonna expect you to do it. It's kind of like something that you have to memorize, the integral of secant of x. Okay, the integral of secant of x is going to be, it's the same thing as its derivative, except it's secant x plus tan x. Okay, remember the derivative of secant of x is secant x times tan x. So it's similar, but different. And then you take the ln of that. So the derivative of secant of x is ln of secant x tan x. There's a proof in the textbook if you want to look at it, but it's going to be much easier if you just memorize it. And then you go from pi over 4 to 0. You can stop the video here and work this out on your own, plugging in ln of secant pi of 4 plus tan pi of 4 minus ln secant of 0 plus tan of 0. Do the math, and you end up with, without a calculator, you end up with square root of 2 plus 1. And that's our answer. So how far, what's the length of this curve? And of course, this is in miles, so we traveled this many miles. That's the length of that curve, ln of square root of 2 plus 1. Alright, finding the exact length of the curve. Find the exact length, or the arc length of that curve right there. We really don't have to look at the graph for this, okay? We know that the formula is going to be L equals from 0 to 1 of the square root of 1 plus the derivative, right, squared of the function dx. So I'm going to do some side work and I want to find the derivative. So it's probably best to do the derivative first and then plug it in, or you can just set it up and then plug it in. So remember, this is just a number, so it's just going to come along for the ride. So what is the derivative of x to the 3 halves? It's going to be, bring down the 3 halves, minus 1, so that's 1 half. And then what's the derivative of 1? 0. So we would stop right here. Let's clean this up a bit. So you would get the 3's are gone. 4 divided by 2 is just going to be 2 square root of 2. And then x to the 1 half is just square root of x. Alright, so that's our derivative. And that is what is going to go into that parenthesis. So it's 2 square root of 2 square root of x. So now before we actually integrate, let's clean this up as much as possible, of course without a calculator, right? Okay, 0 to 1, square root, 1 plus. What is all of that squared? So take it piece by piece. Because it's multiplication, I can distribute that square root, that squared, sorry, to everything inside. So this is 2 squared, which is 4. Square root of 2 times squared, which is times 2. And then square root of x squared is x. So really this is just the from 0 to 1 of the square root of 1 plus 8x. And then you can use u substitution. Because it's linear, you can use u substitution. Because if u is 1 plus 8x, what is du? 8 dx. But I don't have an 8 on the outside, so what do I want to do? I want to get the dx by itself, so divide by 8 on both sides. Alright, you guys can stop the video here and then complete this on your own and see if you get the same answer. So basically, you take out the 1/8, and then the derivative of the square root of 1 over 8x is going to be, the integral, 1 plus 8x raised to the 3/2 divided by 3/2, which is the same thing as saying times 2/3. And then we don't need a plus c because we're going to be deriving it from 1 to 0. You can finish cleaning this up. 2 over 24, which is 1 over 12, of 1 plus 8x to the 3/2 from 1 to 0. Alright, I'll let you guys finish up the algebra, but your final answer is going to be 13 over 6. There's no units here, so that's just going to be our answer, 13 over 6. That's the length of the arc, is 13 over 6. Alright, we're already at 22 minutes. So you, based on the 2 examples we just did, you should be able to do this problem right here. So finish that up. And then these last 2 examples are a little bit tough, so we will do them together. And maybe in class or on a video. We'll see how tomorrow goes. Alright, enjoy.